Right now, you're drifting through an enormous hollow in the fabric of space, a cosmic cavity stretching nearly 2 billion light-years across. Astronomers confirmed its existence back in 2013, yet most of humanity still has no clue that we live inside it. This is the KBC Void, a vast, invisible desert of the universe where matter thins out by nearly 20%. Inside this hollow, the rules of reality twist in subtle ways. Our region of space expands faster than the rest of the cosmos, bending the numbers that define our understanding of everything, from the speed of light to the age of the universe itself. It's as if the cosmos is playing tricks on our instruments, and we've only just realized it. So today, we'll descend into that mystery, the discovery that shook modern cosmology, the strange emptiness that dominates 90% of the universe, and what it means to exist in one of its most isolated corners. If you're ready to question everything you thought you knew about reality, let's begin. 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, were mapping the heavens when they stumbled upon something no one expected. They analyzed the light of over 35,000 galaxies, stretching billions of light years in every direction from Earth. And the numbers didn't add up. Wherever they looked, galaxies were missing. Not just a few, but around 20% fewer than what the standard model of the universe predicts. That shortfall wasn't local either. It extended outward in all directions, forming a spherical region of cosmic near-nothingness, with us eerily close to its center. This wasn't a small gap between galaxy clusters. It was a void on a scale that standard cosmology says shouldn't exist at all. The researchers rechecked their data again and again. They compared surveys from different telescopes, different wavelengths, different angles of the sky. Every time, the same pattern emerged, a vast, underdense region surrounding the Milky Way, so immense that it dwarfs every structure we've ever charted. And when it was confirmed, they gave it a name that sounds modest but carries cosmic weight, the KBC Void, after their initials. But there is nothing modest about what it represents. In the accepted model of the universe, the cosmic web, a vast network of filaments and clusters, is expected to even out when you zoom far enough out. Yes, galaxies clump together, leaving gaps between them. But on the grander scales, the cosmos should appear statistically uniform. That's the principle of cosmic homogeneity, one of the foundations of modern cosmology. Yet this discovery breaks that expectation. A region this massive, this empty, should be virtually impossible according to our simulations of how matter evolved after the Big Bang. To produce a void like ours, the universe would need to start with extraordinarily rare initial conditions, the kind of outlier that occurs perhaps once in 1,000 universes. Some cosmologists estimated it would require a 10 sigma deviation from the average density. So improbable that, statistically, you wouldn't expect to find one even within the entire observable universe. And yet, somehow, here we are. The implications were immediate and profound. If we inhabit such a peculiar spot, what does that mean for every measurement we make about the universe? When we observe distant supernovae to measure cosmic expansion, are we capturing the true rate, or just a distorted version from inside our bubble of nothingness? This idea became known as the void hypothesis, and it offered a bold explanation for one of cosmology's greatest puzzles, the Hubble tension. For years, scientists have measured 2 different rates for the universe's expansion. One derived from the early universe, the cosmic microwave background, and another from observations of the nearby cosmos. The numbers disagree by about 9%. That might sound trivial, but in physics, it's a crisis. Both measurements are extraordinarily precise, and both should be identical. But if Earth lies inside a giant underdense region, the explanation becomes clear. The denser regions outside the void pull gravitationally on galaxies within it, giving them an extra outward push. From our vantage point, that makes everything appear to be receding faster than average. We aren't mismeasuring the universe. We're measuring it from inside a hole. That realization changed everything. But it also left cosmologists uneasy. If our position in the universe is this exceptional, then how much of what we think we know about the cosmos can we really trust? Because what comes next is even stranger. To understand the true nature of our cosmic neighborhood, we must first understand what a void really is. Despite the name, a cosmic void is not truly empty. Emptiness in astronomy doesn't mean the absence of everything. It means the absence of enough. Enough matter, enough gravity, enough light to weave the intricate structures that fill other parts of the universe. Inside a void, there are still galaxies, scattered, lonely islands adrift in a vast, invisible ocean, but they are few and far between. If an ordinary patch of the cosmos holds 10 galaxies in a given volume, that same space within our void might contain only 1 or 2. The rest is dominated by darkness, dark matter, dark energy, and the thinnest traces of hydrogen gas, stretched across unimaginable distances. In regions like this, gravity loses its grip. There simply isn't enough mass to pull things together. The process of cosmic construction, the slow dance of matter clumping into clusters and superclusters, grinds to a halt. Galaxies stop forming in large groups. Structures freeze in time. The void remains. A void. But what makes this profound is not just its stillness. It's what that stillness does to the universe around it. Gravity, the weakest of the 4 fundamental forces, already struggles to shape the cosmos on large scales. Inside a void, it becomes weaker still. Here, dark energy, that mysterious pressure driving the expansion of the universe, takes control. In dense regions, gravity and dark energy compete in a slow cosmic tug-of-war. Gravity pulls inward, trying to hold galaxies together. Dark energy pushes outward, accelerating the expansion of space itself. But within a void, gravity has already surrendered. There's too little mass to resist the outward surge. So dark energy wins, completely. This is why voids expand faster than the rest of the universe. They swell outward like bubbles in an ever-stretching foam. The filaments of galaxies that outline their borders act like walls, dense ridges of matter where gravity still holds some authority. As the voids expand, those walls are pushed farther apart, deepening the emptiness within. The result is a self-perpetuating cycle. The more a void expands, the emptier it becomes. And the emptier it becomes, the faster it expands. The void feeds on its own absence. Astronomers have measured this process directly. By studying the motion of galaxies near the edges of known voids, they found that these galaxies are moving outward faster than cosmic expansion alone can explain. Something is pushing them. A gentle but relentless outward drift, as if the very fabric of space is urging them to leave the emptiness behind. It's not just our void that behaves this way. Across the cosmic web, thousands of smaller voids bubble between filaments of galaxies. Together, they make up nearly 90% of all cosmic volume. If you could zoom far enough out, the universe would look less like a smooth sea of stars and more like a sponge, vast pockets of nothingness divided by thin strands of matter. We live not in a sea of galaxies, but in an archipelago of light surrounded by infinite darkness. The KBC Void is simply the largest and most personal example of this cosmic architecture. It's our local bubble of scarcity, the environment that shapes everything we observe. It influences how galaxies move, how light travels, and even how we calculate the age of the universe. But there's something poetic in this. Most of what exists, even on the grandest scales, is absence. The cosmos is not a universe of things, it is a universe of space between things. And yet, from that emptiness, complexity emerges. Galaxies cluster along the edges of nothing, stars ignite in the shadows of voids, and life arises in one of the rare oases where matter gathered enough to dream about it all. When scientists realized how dominant these voids are, it forced them to rethink what the universe really is. Not a uniform expanse of galaxies, but a vast tapestry where structure and emptiness shape each other, each one defining the other's existence. And so, If we truly live inside a void, the question becomes, what did this emptiness do to us? How did this environment, this cosmic hollow, shape the Milky Way, the formation of our solar system, and the way we see the sky itself? To answer that, we have to go deeper into our own cosmic neighborhood and discover how our local universe came to be carved out of nothingness. When astronomers mapped the galaxies nearest to the Milky Way, they noticed something peculiar. Our home galaxy doesn't live in the heart of a rich supercluster, surrounded by walls of galaxies and vast chains of light. Instead, it sits on the outskirts, on the thin frontier between structure and emptiness. Beyond us stretches a gulf of darkness known as the local void. The local void is a smaller hollow nested inside the vast KBC Void, a kind of cosmic subbasin carved out of the greater underdensity. It begins just beyond the Virgo cluster and extends tens of millions of light-years in every direction. At first, scientists assumed it was simply a region we hadn't charted well enough. But as surveys grew more complete, it became clear that the emptiness was real. The local void isn't an illusion of missing data. It's a genuine cosmic cavity, largely barren of galaxies, its edges defined by a few lonely star systems that seem to drift away from it. This has direct consequences for the Milky Way. Gravity doesn't pull evenly in all directions. On one side of our galaxy lies the mass of the Virgo supercluster, tugging us toward its dense heart. On the other lies the vacuum of the local void, a place so empty that it exerts a kind of gravitational absence, a pull in reverse. The result is motion. Our galaxy, along with the entire local group, is moving at hundreds of kilometers per second relative to the cosmic background, drawn one way by gravity and pushed the other by emptiness. It's as if the universe itself were inhaling, matter flowing from nothing towards something. Every galaxy on the boundary of the void experiences this subtle migration. They fall toward the denser walls, sliding away from the hollow like dust carried by a cosmic wind. Over billions of years, this quiet flow sculpts the cosmic web, draining voids of matter while thickening their walls. So, in a sense, the Milky Way is surfing the edge of nothingness, carried along by the expansion of an invisible bubble. When we look at the night sky, it feels filled with stars, nebulae, and galaxies, a crowded theater of light. But that vision is deceiving. For every glimmering point we can see, there are stretches of absolute blackness hundreds of millions of light-years wide. Our view of the universe is like standing on a single island at night and mistaking it for a continent. Yet it's in this quiet corner that complexity thrives. Because the void around us expands slightly faster than average, it gives our region of space a gentler gravitational environment. Galaxy collisions happen less frequently here. The Milky Way has had time, billions of tranquil years, to develop spiral arms, nurture stable planetary systems, and allow one of its worlds to wonder about all this. Life may owe its existence to the emptiness outside our cosmic door. If our galaxy had formed in a denser region, near the violent cores of rich clusters, constant gravitational interactions might have torn planets apart before life could gain a foothold. The stillness of the void may be the reason consciousness ever had time to emerge. This idea adds a new layer to the so-called cosmic principle, the assumption that our place in the universe is not special. But what if it is? What if the conditions that allowed us to exist are as rare as the void itself, an improbable calm in a sea of chaos? It's an unsettling thought. For centuries, astronomy has taught us humility, that Earth is not the center of the universe. But if our position truly lies in such a statistically unlikely void, the story reverses slightly. We might inhabit one of the most peculiar neighborhoods in all of space. Not central, not privileged, but profoundly unique. The local void, the KBC Void, and countless smaller cavities are not isolated oddities. They're part of a pattern. The cosmic web is an enormous mosaic of contrast. Structure born beside absence, expansion beside collapse. And while gravity sculpts the bright filaments, it's the voids that provide the canvas on which the universe paints its story. To understand how this grand architecture came to be, we must go back, far back, to the beginning. To a time before galaxies, before atoms, when the entire universe was nothing but ripples in a sea of energy. It's there, in the first fractions of a second after the Big Bang, that the seeds of these voids, including our own, were planted. To understand how we came to live inside a cosmic hollow, we have to return to the very beginning, to an age before stars, before atoms, before light itself. The universe was once a perfect blur. 13.8 billion years ago, all matter and energy were compressed into a state so dense that the laws of physics as we know them begin to fail. Then, in a single instant, space itself began to expand, not into something, but as something. This was the Big Bang. For a fleeting moment, less than a trillionth of a second, the universe grew exponentially in size during a phase known as cosmic inflation. Tiny quantum fluctuations, ripples in the very fabric of reality, were stretched across vast distances. These minuscule differences in density would later become everything, the scaffolding from which galaxies, clusters, and voids would form. In that primordial chaos, some regions had slightly more matter, some slightly less. The differences were infinitesimal, 1 part in 100,000, but over cosmic time, gravity amplified them. The dense regions drew in more material and became the luminous filaments and clusters we see today. The underdense regions, the negative imprints, became the voids. Emptiness was not an accident. It was written into the universe from the very beginning. As the young cosmos cooled, matter began to slow its frantic motion. Hydrogen and helium atoms formed. Gravity started pulling these atoms together into the first dark matter halos, invisible structures that acted as the skeleton of the cosmic web. But in the regions where density was low, gravity didn't have enough to work with. Those areas expanded faster, thinning out even more as nearby matter migrated toward denser neighbors. Each small underdensity became a bubble, and those bubbles grew. Some merged, forming the vast cosmic caverns we now call voids. Others collapsed into filaments and nodes, creating a vast contrast of light and darkness across the universe. By the time the first stars ignited, 100 million years after the Big Bang, the Great Divide was already in place. Regions destined to be galaxies, and regions destined to remain empty forever. The pattern of those early fluctuations can still be seen today in the cosmic microwave background, the faint afterglow of creation that fills all of space. When astronomers measure its tiny variations, they're looking directly at the seeds of every galaxy and every void that would ever exist. The fingerprints of the universe before time had truly begun. Over billions of years, as matter clumped into galaxies and clusters, the voids expanded alongside them, sculpting the large-scale structure of the universe like bubbles in foam. But this expansion didn't stop. Even now, the voids continue to grow, driven by dark energy, the mysterious force that accelerates the expansion of space. It's a process without end, an eternal separation. The rich get richer, the empty gets emptier. The cosmic web stretches thinner with every passing eon. If we could watch the universe unfold in fast forward, we'd see the bright filaments receding, like veins of light dissolving into darkness. The voids swell, merge, and devour the spaces between galaxies. Eventually, only a few isolated clusters will remain. Islands of matter adrift in an infinite sea of nothing. In this far future, the night sky will fade. Galaxies beyond our local group will vanish from view, their light redshifted beyond detection. The cosmic web will disintegrate, leaving behind vast, lonely bubbles of space expanding into silence. The story of the universe is not just one of creation, it's one of erosion, of light being swallowed by the dark, of structure giving way to emptiness. And yet in that emptiness, there is meaning, because the same physics that carved out the voids also gave rise to the galaxies that question them. The forces that created our isolation also made consciousness possible. We are not apart from this cosmic process. We are its most self-aware expression. But the story of the void doesn't end with its birth. The deeper question remains. How does this immense hollow shape what we see when we look out into the cosmos today? How much of what we think we know about distances, time, and even the fate of the universe is distorted by the emptiness we live in? To find out, we must explore how the KBC Void bends our perception of reality itself. Because in the vast darkness surrounding us, light does not behave the way we think it should. Light is the oldest traveler in the universe. Every photon that reaches our eyes has spent billions of years crossing the cosmic landscape, slipping through clusters, weaving between filaments, and gliding across endless voids. It carries with it a message from the past. But like any traveler, its path is shaped by the terrain it crosses. And our terrain is not what it seems. Living inside a giant cosmic void means that space itself around us is expanding faster than average. Every beam of light entering our region from denser surroundings stretches just a little more as it travels through this underdense bubble. This stretching, known as cosmic redshift, makes distant galaxies appear farther away and moving faster than they truly are. The deeper we peer into the universe, the more we rely on these redshifts to measure its expansion. But if our local space is distorted by emptiness, then every one of those measurements carries a hidden bias. When astronomers in the early 20th century first realized that galaxies were receding from us, they interpreted that motion as universal, the same everywhere for everyone. But what if that's not quite true? What if our region is expanding just a little quicker because we live in an underdense zone? That's the essence of the KBC effect. From inside the void, the universe appears to accelerate more than it actually does. This illusion could help explain one of the greatest puzzles in modern physics, the Hubble tension. The Hubble tension is a simple problem with enormous consequences. Depending on how we measure the expansion of the universe, we get two incompatible answers. Observations of the early universe, encoded in the cosmic microwave background, suggest one rate. Observations of nearby galaxies and supernovae, the universe as it looks today, suggest a faster rate. The numbers disagree by roughly 9%. Not much at first glance, but in physics, that's a crack in the foundation. For years, cosmologists have debated what it means. Is our model of the universe incomplete? Are we missing a new kind of particle, a hidden force, a correction to dark energy itself? Or are we simply standing in the wrong place? If the Milky Way lies inside a vast underdense bubble, the KBC Void, then galaxies around us are being pulled outwards slightly faster by the gravity of the denser walls beyond. From our perspective, that outward drift mimics a faster expansion of the entire universe. But it isn't universal. It's local. We're not observing the cosmos from an average position. We're measuring it from inside a distortion. This doesn't make the data wrong, only our assumption that our view represents the whole. In reality, it's as if we live inside a magnifying lens, one that subtly warps the light of the universe as it passes through. To understand this effect, imagine floating in a bubble of thin air surrounded by thicker atmosphere. Sound waves entering the bubble would change speed as they cross the boundary, bending slightly, distorting the pitch. To an observer inside, the world beyond might sound different, not because the universe has changed, but because their environment has. Light behaves the same way in space. As it travels through regions of varying density, its energy shifts. Photons climbing out of dense regions lose energy. Photons entering voids stretch their wavelength, redshifting into longer, softer light. From our position, surrounded by emptiness, every distant galaxy appears slightly more redshifted than it truly is. This means that our cosmic yardsticks, the distances we infer from brightness and redshift, are subtly skewed. The universe looks older, larger, and faster expanding than it might actually be. For decades, cosmologists have treated the cosmological principle as sacred, that the universe looks the same everywhere, from any vantage point. It's the bedrock assumption that allows us to treat our corner of space as representative of the whole. But the KBC Void challenges that idea. If we inhabit one of the largest underdense regions ever detected, then our measurements are not typical, and that means our cosmological models might need to change. This doesn't invalidate the Big Bang or the expansion of the universe. It simply adds a layer of complexity, the recognition that where we stand matters. Perspective shapes truth, even in cosmology. Some researchers propose that once we account for the KBC Void's influence, the Hubble tension nearly disappears. The early and late universe fall back into agreement. The crisis fades, not because new physics is found, but because we realized we were measuring from inside a cosmic mirage. But not everyone agrees. Many scientists argue that the void alone can't explain the full discrepancy. To settle the debate, we need sharper measurements, deeper surveys, and a clearer map of the structure surrounding us. And that is exactly what the next generation of telescopes, the James Webb Space Telescope, Euclid, and Vera Rubin Observatory, have begun to deliver. They're revealing not just galaxies, but the invisible web of gravity itself, showing how light bends, slows, and stretches as it passes through the uneven texture of space-time. And what they're finding hints at something even deeper, that the voids of the universe might not be empty at all, but filled with energy we can't yet understand. At first glance, a void should be the quietest place in the universe. No stars, no dust, no heat, nothing for light to touch or gravity to shape. But the deeper astronomers look, the more they realize that emptiness is not nothing. It hums with invisible energy. This unseen presence is called dark energy, a force that seems to accelerate the expansion of the universe itself. It is not a wind that blows through space, but a property of space. Every cubic meter of vacuum contains it, constant and relentless, no matter how much the universe grows. In dense regions, gravity gathers matter together, fighting this expansion. But inside a void, gravity has surrendered. Here, dark energy dominates completely, stretching the fabric of space faster than anywhere else. So paradoxically, the emptiest regions of the universe are also the most active, not with matter, but with expansion. They are engines of cosmic growth. Scientists describe this balance with an equation: Einstein's cosmological constant, the simplest form of dark energy. It represents the pressure that fills the vacuum, pushing the universe apart. For nearly a century, physicists argued about whether this constant was real or merely a mathematical trick. Then, in 1998, two teams observing distant supernovae proved it beyond doubt. The universe is accelerating and dark energy is real. But they may have underestimated where that acceleration comes from. If voids expand faster than dense regions, and if voids fill nearly 90% of cosmic volume, then perhaps the large-scale acceleration we see is not uniform at all. Perhaps it is the sum of countless expanding voids, millions of bubbles of nothing, growing and merging, each one pushing on the next, until the universe itself appears to race outward. This idea, called back reaction, suggests that the structure of the universe can influence its overall expansion. Space is not smooth, and its roughness matters. Voids are not passive bystanders. They are the architects of cosmic acceleration. If this is true, then dark energy may not be a mysterious new force at all, but a shadow cast by geometry, the visible effect of emptiness itself taking over.